Alright guys, in this video segment we're going to take our concept of stoichiometry and solving for amounts of product produced and take it one step further. Okay, so we finished up the other day talking about the moles, the mole bridge chart. If you take a look at the screen, again we're working through this process where I can start you at a volume of a solid or a liquid, at a volume of a gas at STP, number of particles or moles. And any of those starting points you should be able to solve all the way across and give me number of particles, volume of a gas at STP, the mass, moles, or volume of a liquid or solid if we use density. So again, don't be afraid to use this chart as you're practicing to get through your pathways. But remember, you have to get weaned off of this chart as we get into testing time. All right? But everything funnels through this mole ratio. So that has to come from that balanced chemical equation. Now the next step that we're going to take is what happens if we have a reaction that we know the values of two different starting points. For example, what would happen if we had aluminum reacting with mercury nitrate and I had, let's say, 100 grams of aluminum and I mixed that with a solution that contained 1,000 grams of mercury nitrate. Okay, so what makes this problem different is now we know the starting point, or we have a limited amount of both of our reactants. Up until this point, everything has had an excess of something. We've kind of ignored one of our two reactants, but now we're going to funnel in what happens when we don't have an excess of one thing and we have limited amounts of both. To do that, we call these problems limiting reactant problems. Okay, in this process, we need to figure out which of these two, the aluminum or the mercury nitrate, is going to limit the reaction, or basically which one's going to run out first. Okay, so imagine that you are working at a McDonald's, or you're working at some sort of restaurant and you're making hamburgers, you're making your food, making your meals, and at some point, let's say you worked at a fancy restaurant and you had the special of the day, and the special included, you know, a baked potato, it included you know, some sort of like Peking duck or filet mignon, or you know, some sort of meat with that. And it also included, let's say, a side of asparagus. I don't know. Now, if you're making that meal and it's a special, if you run out of any one of those three things, you no longer can sell it as a special. So you basically have run out. So that what happens is we say that once that happens, you've limited the reaction. Okay. Same thing happens in anything in chemistry. If you're running a combustion reaction, if you run out of gas, the combustion stops. If you run out of air, the combustion also stops. The process ends. This idea actually transcends into the business world too, where if you look at, you know, retail sales and those kind of things, there's a reason why when you walk into a store in the mall, if it sells both guys and girls clothes, that the guys area is about 1/2 the size of the girls area is, because those companies have figured out that they sell more girl clothes, so they might as well stock their stores with more girl clothes, so that way they don't run out of one versus the other. Same thing at Thanksgiving time. It's not a surprise that Cub Food stocks up on turkey when it comes to Thanksgiving time. Well, because they know that they're going to sell more of it, and once they run out, well, then they lose their customers. The whole idea of going to Cub Foods ends if you can't buy your turkey there. So they use this concept of limiting reactant, maybe not in a chemistry standpoint, but from the same idea of ratios and amounts you need to keep a process, your sales going. So we actually can apply this to other disciplines if we needed to. Now, in terms of our problem, where we have 100 grams of aluminum and 1,000 grams of mercury nitrate, you might think, well, you have 1/10 of this, so aluminum must run out first. That idea can cause problems because we have a certain mole ratio and we have different masses here. So in reality, you can't just look at it in that simple context. You actually have to break the problem down and solve for one of your products to see what one actually limits the reactant. Okay? So if we go to our screen, let's get through some terminology. Whatever limits the reaction, we call that the limiting reactant. It runs out first and it dictates the amount of product that can be produced. So whatever runs out first, that determines how much you can make. The excess reactant is more than you need, and there'll be some of that left over once the reaction is done running and you've run out of your limiting one. Okay? Now here's the cool thing. There's no new math with this. All we do is the same thing we've been doing, but we just do it twice and compare our answers. Okay? So let's go to the board and we'll work out our problem. problem and see what is limiting, what's excess, and how much product we actually can produce here. Okay? So we have 100 grams of aluminum, we have 1,000 grams of mercury nitrate, or mercury 1 nitrate. So I'm going to set my problem up, take my 100 grams of aluminum, 1,000 grams of mercury nitrate, and I want to say I have 100.0 grams of aluminum, and I have 1,000 grams of mercury nitrate. And let's say for this problem, we're trying to figure out how many milliliters of mercury we're making. Okay, so let's solve for milliliters of mercury. So we add a little bit more complexity to the problem. So our first step for each one of them is to go from grams to moles. And then work our way through the mole bridge, grams, and so forth. So I'm going to do all of the aluminum one first, now that we got it started, and then I'll come back and do all of the mercury nitrate one next. So our next step here is a mole ratio. Oh, wait a minute. I didn't balance the chemical equation. Okay, we got to do that. So before I can get any further in my math here, I need to know what goes in these blanks here. So balancing the equation has to be done before I go into the stoichiometry. So I have 1 nitrate, 1 mercury, 1 aluminum. Here I have 3 nitrates, so I have to triple this, which means I triple my mercury, but my aluminums can stay the same in my process. So I'm balanced now, which then tells me that my aluminums, for every 1 mole of aluminum, I'm going to get 3 moles of mercury. And then for every 1 mole of mercury, I get 200.59 grams of mercury. So this is our atomic mass off the periodic table. And then finally, to get to milliliters, I need to use density. So I know that for mercury, the density of mercury is 13.54 grams of mercury per every 1 milliliter of mercury. So this is a value that you'd have to look up or be given to you in a problem. So I know my grams per milliliter or my density, and then now I can solve for my final answer in milliliters of mercury. Do the same thing for our mercury nitrate. It's going to be the same number of steps, just some different things to fill in. So I know that for every 1 mole, actually no, it's 3 moles, so I have a 3 right here. So for every 3 moles of mercury nitrate, I make 3 moles of mercury. Okay, so it's a 3-to-3 ratio, so mathematically they do cancel. But I like to show it just to remind myself I did that step. And then for every 1 mole of mercury, I get 200.59 grams of mercury. And then 13.54 grams of mercury for every 1 milliliter of mercury. So we get 262.60 grams per mole of mercury nitrate. Now I didn't put that one in for the aluminum either. So aluminum, if we look that up, is 26.98 grams per mole of that one. So now I have all my values put in and I'm ready to calculate. So we'll run this thing through the calculator and we'll get an answer for that. So here we go. Okay, so once we do all the math, run both of the calculations through, we see that we get 164.7 milliliters of mercury out of 100 grams of aluminum. And out of the 1,000 grams of mercury nitrate, we're going to make 56.242 milliliters of mercury. So what that tells us is that there's enough aluminum here to make up to that much. but there's only enough mercury nitrate to make this much. So as soon as we hit 56.42 milliliters as the reaction runs, as soon as that number gets hit, this is now gone. So when this is gone, the reaction stops. So even though we could make up to that much for the aluminum, as soon as we hit this number, it turns off. It's kind of like, as soon as you hit this number, you ran out of gas and the car quits running. That's where the reaction stops. So this is how much we can actually make. This value is invalid. Okay? So we always pick the lower number between the two. It's always the lower value is the one that is our answer. Okay? When you're recording these, make sure that you do this, because if you give me both answers and don't tell me the right answer, I'm going to assume that you don't understand that one of these is correct and one of them is not correct. So cross one out, circle one of them, tell me that this is the right answer, this is not, some way of indicating that you understand that this is how much we really can make here. Okay? Now, you could take it one step further and we could say, well, if this is how much we've made, how much of the aluminum was used? Because we didn't use all 100 grams. Some of it got wasted. So you could run the process and actually figure out how much was wasted. There's more than one way to do that. You could start with this number and actually solve towards aluminum, or you can start with this number and solve towards aluminum. Okay? For my purposes, I want to start with this number and solve towards aluminum. So what I'm basically saying is, if I used 1,000 grams of mercury nitrate, how many grams of aluminum should have I used to match up? Again, the math is not new. Same process, okay? So let's work through and solve for how much aluminum should have we used. So I'm solving for grams of aluminum. I have most of my numbers already here. Now it's just filling in and calculating. The step for mercury nitrate is the same. My ratio between aluminum and mercury nitrate is known from here. So I have 3 moles of mercury nitrate for every 1 mole of aluminum. And then I get 26.98 grams per mole of aluminum. Okay? We run this calculation and we get 34.25 grams of aluminum. So the correct stoichiometric ratio is, if I'm going to use 1,000 grams of mercury nitrate, I should have only used 34.25 grams of aluminum, and that would have been the right amount to use. Okay? So how much aluminum was left over, or how much aluminum was wasted? Well, now we used 100. We should have used 34.25. So to figure out how much was wasted, or how much leftover aluminum we have, we just subtract the two. So 100 minus 34.25, again, you probably could do that one in your head. But just to make sure, we get 65.75. Okay, so this is the aluminum used. This is the aluminum left over. Or sometimes we say it's the aluminum that was wasted in the process. Okay? So a big problem, a lot of stuff to do, but if you look at it, it's all the same math we have been doing. It's just now applying this concept that you could have limiting amounts of both of your reactants. Okay? So that's one practice problem. We have more practice problems for you guys to do in class, so please make sure you bring not only your notes, but also make sure you have your worksheets to work on that in class, guys. Okay, guys, that is our limiting reactant stuff. Thank you for your time.